Well, without hydrogen bond, life would be impossible. I think everybody knows this example. No? Everybody knows here DNA. Everybody knows that one main feature is the aggregation of a DNA, and this is fixed by hydrogen bond, weak intermolecular interaction. Not covalently bonded, we are intermolecular, weak, non-covalent bonds. And looking to this hydrogen bond, what we have an amino function here on the one side, NH, and on the other side we CO double bond. And this is here the dominating key function of DNA, the aggregation of DNA. This is called amide pattern. Yeah? I would say the most important hydrogen bond we know, and very nicely you see how important it is for our life. Well, in the introduction I said let's talk about definition. What are hydrogen bonds? And if you look in an older dictionary, you will find something like this. No? This is the dictionary, this is in this case is for 1971. And you see a weak electrostatic chemical bond which forms between covalently bonded hydrogen atoms and a strongly electronegative atoms with a lone pair of electrons. Well, older dictionary, and the most important keywords are here electrostatic chemical bond, strongly electronegative atom, and lone pair of electron. I would say this is an extremely restriction talking of a hydrogen bond, and this extremely restriction of hydrogen bonds, well, this was the background, the reason several scientists think about a new definition of hydrogen bond. And I would say the most interesting or the best definition of hydrogen bond is written here. The hydrogen bond is an attractive, it's very important, attractive interaction. Attractive means we are talking about an energy, yes? Attractive interaction between a hydrogen atom from molecule or molecular fragment XH, in which X is more electronegative than H, and an atom or group of atoms in the same or different molecule in which there is an evidence of bond formation. Attractive interaction and bond formation. And X is more electronegative. You see, it is a much more weaker definition of hydrogen bonds and help us much more to use hydrogen bonds in crystal engineering. But we talk about restriction. I said the older one was a restrictive definition of hydrogen bond. The newer one is more or less a little bit weaker, but on the other side where we have criteria, a list of criteria which should fit to hydrogen bonds. And this list was also published by the authors here in this from 2011 in this contribution. Okay, have a look on this list of criteria. First of all, speaking about the form, the type of hydrogen bond. No? Forces, attractive interaction involved in formation of hydrogen bonds include could be electrostatic origin, charge transfer between donor and acceptor, or dispersion. Second point, you see it here, is X and H are covalently bonded. Here you see, covalently bonded. X, H are polarized. And with here, a hydrogen bond, we are talking about H epsilon, is increasing with an increase in the negativity of X. And we are talking mostly, this is the best model, the optimal model of hydrogen bond. You see it here, X, H, epsilon, Z. Okay? And you see it, I draw here, I figure out the angles. On one side we have X, H, epsilon, should be linear, 180 degree, and H, epsilon, Z, this angle should be around about 90 degree. What are the impacts of this criteria? Impacts are, looking, for example, with spectroscopic methods, we should see in the infrared spectrum, we should see an effect. This effect is a redshift of this XA stretching frequency, a new vibrational mode associated with this here, with the hydrogen bond. So two effects, shift of XH and additionally appearance of a new mode of a hydrogen bond. Second thing, we can use NMR spectroscopy, and we should find a significant NMR signature of this pattern. Mostly we see brightness of the signals for hydrogen, because it's not located in one position, it is delocated about the space, bigger range. And this has an impact on the energy. The Gibbs energy of formation of a hydrogen bond should be greater than the thermal energy of the system for the hydrogen bond to be detected experimentally. Yes. There should be an effect on the Gibbs energy. Well, we have seen DNA, we have seen this amide pattern, this typical hydrogen bond, mostly typical hydrogen bond, most important hydrogen bond. But on the other side, there's a broad field of hydrogen bond. And we will not look to each part of each type of hydrogen bonds. It's really impossible to do it here in this lecture series. But please don't forget, we are not only talking of one point hydrogen bond like in the DNA, or with only the amide pattern. Whereas, for example, this is a contribution from Allen, 1999, and there's a huge number of different hydrogen bonds. In this case, we have several 2-point hydrogen bonds. You see it here, for example, 2-point here, 2-point, and so on. This is only a short list, very short snapshot of possible hydrogen bond. Much more interesting for us now is to think about the strange and the usage of hydrogen bond. So we can say, well, let us divide hydrogen bond in strong, moderate and weak hydrogen bonds. I think this is useful classification. Okay, strong hydrogen bond, mostly ionic hydrogen bond. Ionic hydrogen bonds are formed by a group containing electron density deficiency on the donor and an excess of electron density in the acceptor groups. This is mostly seen in ionic species. Moderate hydrogen bond, generally formed by neutral donors and acceptor groups, in which donor atoms are electronegative to the H atom, and the acceptor atoms have unshared lone pair electrons. And the last thing are weak hydrogen bonds. Are formed when the hydrogen atom is covalently bound to a slightly more electronegative. So mostly we are talking about the difference in electronegativity, or when the acceptor has no lone pair but has p electrons, for example. Strong, moderate, weak. And this is a very nice table of different properties of his hydrogen bond. Now it's called, in this case we said strong, moderate, weak. In this case it's very strong, strong, weak. Anyway, we have three classes. No? This is information. Three classes, three types of hydrogen bonds. No? Energy, in this case, is kilocalorie. Yeah, very strong, 15-14 kilocalorie. Strong, much less energy, 4-15, and weak, below 4 kilocalorie. This is very weak. In examples, here you see this typical ionic species. We talk about this. This anion, difluorine hydrogen. Anion, strong. You see it here with for the second one here. This is this amide unit I spoke about. And on the other side here, CHO. We talking about crystal database, Cambridge structure database, talking about how can you use it. This is a weak hydrogen bond. You see, as I said, electronic, spectroscopic impacts, for example here with IR shift, you see it now, and so on and so on. Important is, if you're going here, scroll a little bit downstairs, an effect on crystal packing. This is very important. Very strong hydrogen bonds are not really useful in crystal engineering because mostly we have insulated units. We do not link with other units of a crystal structure. I've shown you in the case of this anion here. You have seen absolute not useful crystal engineering. Much more useful are moderate or from a second class hydrogen bond. No? Well, here I signed with significant properties. I would say the bond energy. This is significant. And I assign here the distance of X, the donor and acceptor range. Yes, you see it here. If you have a weak hydrogen bond, you have an enlarged distance. And the angle. You see it here, no? We're talking about, I've shown you that mostly, the aim is to get a linear angle around about 180 degrees. You see it here in the case of strong, the second class is 130, 180 degrees. In the case of weak, yes, randomly, everything is allowed. If you look to this table, you see some other values, and I would say some of them are only observable if you have a really high quality single crystal structure with very high quality. And in this case, you can discuss, interpret, analyze bond lengths of involving hydrogen, yes, and you can think about enlarging bond lengths, for example, something like this. No? So once again, only observable or useful if you have a very high quality X-ray crystal structure. Good. I've shown you, you remember the slide, you have seen it, talking about Cambridge structure database, where you nicely you can see the case, for example, of strong hydrogen bond. We have a small area of possible angles and a small area of possible hydrogen bonds with length, distance. On the other side, talking about a weak hydrogen bond, you see everything is nearly allowed. Angle from 180 degree to 100 degree, and yes, if you look to the range of distance between 2.2 to 3 Once again, very nicely, you can see here, this was here, the length and the angles. Can show it very nicely. Okay. Have a closer look on hydrogen bond. Well, this is the pattern we are talking about. CH or XH, whatever you want. On the other side, epsilon and residue, whatever you want. So, and we have two parameters we can have a look. We have D, hydrogen bond, and we have a capital D, distance of the acceptor and the donor. Yes? And what we see is, if we have a hydrogen bond, which has influence on, if we have a hydrogen bond, there should be an influence here on the capital D, the distance of donor acceptor. When we have a shortness, it should be shorter than the double van der Waals radii. It's shown here in the amide. We find here distances between 2.5 2.8 with a typical distance amide pattern, and it is significantly shorter in comparison to the van der Waals radium. And the second thing is the angle. I said should be 180 degrees, but mostly, if you look to the crystal packing, if you look to the crystal structure, you will see mostly. Also in the case of strong hydrogen or moderate hydrogen bond, mostly you have around the meridian is around about 165 degrees. The reason is very easy, but mostly if you look to the crystal structure where additionally acceptor units partner available in the near environment of a hydrogen bond. Yes. And this disturb this hydrogen bond and leads to a shortness of the angle. No, mostly 165 degrees. Now, one step further, looking to the hydrogen bond, looking to the values. We talk about this phosphoric acid. And this is a crystal structure, phosphoric acid. You see here we have this an OH in this covalent bond, and there's an interaction here to oxygen of the neighboring. Here is our value. This is capital D, donor acceptor distance. Here's the hydrogen bond. Two parameters with the covalent bond, and this is the intermolecular interaction. But have a look carefully. There's a bracket at the end of the values. What's that? These values are extremely important because these values say something about the quality of a structure. ESD, estimated probable error. Yeah? Give information on the accuracy of a length, plus minus error, and only last digit is meaning. Okay? So if you now compare this value 2.592 in the last digit plus minus 2 with 0.79 last digit plus minus 3, there's a difference factor 10. Yes. In this case the second digit this means plus minus 3. In this case the third digit this means plus minus 2. There's really a large difference in the quality of a contact or distances. So please, in general, not only in this course, in general, if you analyze any bond lengths, yes, please, before you start discussing anything, have a look on the ESD. sometimes if you have very large EST, and this is for example direct with primary, first digit here, error with a primary digit, so it is nearly, it makes no sense to discuss something like this. No? Okay? Next question. D value in contrast to capital D value. Which value could the series interpret? Which value should you have a look if you think about crystal structure design and so on? No? D and capital D. What do you think? Well, to answer this question, we must have a look on X-ray crystal diffraction. Yes, the problem is that mostly it is not possible to localize the hydrogen atom in crystal structure determination. Why? The background is X-ray crystal structure diffraction is based on the interaction of a wave X-ray and the electrons. Yes. Higher electron density means higher interaction. In the case of hydrogen, we are talking of an interaction of X-ray with one electron, not more. The question is, where is the electron located? You know that the electron is not diagonally located in the atom. That's the first thing. Second thing is, using X-ray methods, the hydrogen bond of hydrogen lengths are always consistently shorter than the true value. That means what you see, what you get from a crystal structure is not true. That's not the exact distance. Why? I'm showing here. This is donor hydrogen covalent bond. No? And this is what happens in a crystal. No? So what you see is a libration depending on two positions. Here. Yeah? Well, and what you see is, what you get is here the average distance. What you get is this one here. The blue and the red, the distance of the blue and the red ball. What is what you see is. But true is this distance, the blue and the open circle. No? Okay? This is the reason you always is a little bit smaller. Okay, that's it. The first part of hydrogen bonds. See you for the second part.